The title of this presentation is What Does It Mean to be Infinitesimally Small in Calculus? This is one of the cornerstone concepts of calculus. It's also arguably one of the more confusing or difficult concepts in calculus, and I'm going to explain it with 3 examples. The first example involves a linear function. Discover how a simple straight line unravels the mystery of infinitesimals. The second example will be with nonlinear functions. The third example will be with a definite integral. Witness how the integral stitches together an infinite mosaic from infinitesimally small pieces, revealing the whole picture. All right, so example 1. Let's discover how a simple straight line unravels the mystery of infinitesimals. In this example, I'm looking at a linear function y equals 3x. This is a standard linear function. It has the form y equals mx plus b. The function is plotted on the left, and I've put one point on the function. I've called it a, and this is the point 1, 3. When x is 1, the y value is 3. Okay, now let's calculate the slope of the line passing through the point 1, 3, given delta x equals h equals 1. So delta x is a change in x. In calculus, it's typically called h. And in this particular problem, I'm setting it equal to 1. We know the function is y equals to 3x. We're given one point, which is x1, y1 equals 1, 3. The second point, we know h or delta x is equal to 1. That means x2 is equal to 2 because it's 1 plus 1 is 2. And if x2 is 2, you can plug it in and get the y2, and then y2 is 6. So now we have 2 points. The definition of the slope of a linear function, the slope of any function actually, is y2 minus y1 divided by x2 minus x1, or change in y over change in x, rise over run. This is the definition of the slope. And for this particular problem, the slope is 3. Next, let's calculate the slope of the line passing through the point 1, 3, but now delta x, or h, is going to be 0.5, not 1 like it was in the previous part. So here, this is point A. Here is point B from the previous part of the problem, but now we're moving closer, and we're going to calculate the slope with the point C1. And it should just be the point C, but I wrote it C1. So x1, y1 is 1, 3. We have that already. x2, delta x is 0.5, so x2 is 1.5. You add 0.5 to the 1, and then y2 is going to be 3 times that, which is going to be 4.5. The slope is y2 minus y1 over x2 minus x1, and if we calculate the slope, we get 3 once again. So if you calculate the slope between A and B, you get 3, and if you move B closer, and now it becomes C1, to calculate the slope between A and this point C1, you still get 3. Now let's calculate the slope of the line passing through the point 1, 3, but here we're going to use delta x is equal to 0.1. The previous example, we had C1 here, but now we're moving closer and we're going to use the point D. So x1, y1 is still 1, 3, x2 is 1.1, y2 is 3.3, and the slope is 3 once again. So here are some key takeaways from example 1. The point x2, y2 can approach x1, y1 arbitrarily without affecting the value of the slope calculation. This illustrates the concept of being infinitesimally small. Consequently, points x1, y1, and x2, y2 can be chosen as close together as desired. Their distance can be as small as you want it. It can be 10 to the negative 19, or it can be 10 to the negative 100, and there's no change in the computed slope. No matter how close the points are together, they're infinitesimally close because it doesn't matter how close they are. Regardless of how close together they are, the slope is the same. All right, now let's move on to a more difficult example with a nonlinear function. The derivative involves dividing by infinitesimals and reveals subtleties of nonlinear functions. For example 2, I'm going to be looking at the function y equals x squared. This is a standard parabola, simple parabola. I've plotted the parabola on this page. I also zoomed in at one point on the parabola, which is the point x equal to 1 and y equal to 1. We'll be calculating the secant line through that point. Finding the slope of a secant line to a function through a given point. This is example 2 continued. Given a function, a point, and an h value, one can calculate the slope of the secant line to a function. A secant line is a line that cuts through 2 points on a function. This line I've drawn here is the secant line, and the secant line to the function y equals x squared, and it goes through point x1, y1. One of the points is x1, y1. That's equal to x1 f of x1. And the second point is x2, y2. x2 is x1 plus h. You're given h. And y2 is f of x1 plus h. The slope is defined to be y2 minus y1 divided by x2 minus x1. And therefore, this function here, f of x1 plus h, minus f of x1 divided by h. This is a formula that tells you the slope of the secant line if you're given a value x1, h, and a function. If, for example, for the function y equals f of x equals x squared, the slope of the secant line would equal x1 plus h squared minus x1 squared divided by h. And so if you were given an x1 value and an h value, you could then calculate the slope of the secant line. On this slide, I'm going to go through an example where we find the slope of the secant line to the function y equals x squared through the point 1, 1 squared, given that h is equal to 1. The givens here are that x1 is equal to 1, h is equal to 1, and y is equal to x squared. One of the points is x1, y1, and that's the given point, which is 1, 1. This is one of the points that the secant line is going to go through. Now we're given that h is equal to 1, so therefore the other point is going to be 2, 4, and that's this point right here. For delta x equals h equals 1, the slope of the secant line passing through point 1, 1 is 3. Now let's repeat the previous example, but we're going to use a point closer to 1, 1. H is 0.5 in this case, it's not 1. In this example, what we're given is x1 is 1, h is 0.5, it's the same function, y equals x squared. Now we have 2 points, x1, y1, the given point, 1, 1, and x2, y2, 1.5, 2.25. We can use these to calculate the slope. You can also use the formula I calculated a couple slides ago, and what you find is when the point gets a little bit closer, the slope changes, the slope to the secant line changes, and now the value is 2.5. For delta x equals h equals 0.5, the slope of the secant line passing through point 1, 1 is 2.5. Repeat the previous example, but now use h equal to 0.1. Point x2, y2 is getting closer and closer to point 1, 1, which in this case is x1, y1. Now the slope is 2.1. On this slide is a table of secant line slopes through the point 1, 1 on the function f of x equals to x squared. H is in the left column, the slope of the secant line is in the right column. Once h gets very small, the slope of the secant line stabilizes and it no longer changes. As the value of h decreases, the slope of the secant line initially undergoes significant changes when h is large. So in this column, this is h, and when h goes, for example, from 1 to 0.5, the slope of the secant line changes a lot. It goes from 3 to 2.5. However, beyond a certain point, further reduction leads to progressively smaller changes in the slope. There exists a threshold value of h, below which the calculated slope of the secant line is essentially the same. Here's an example to help you understand this. Assume that 10 to the negative 6 is a threshold value of dx below which all other slopes are considered the same. To find the slope of the tangent line of f of x equals x squared at the point x equals 1, we need 2 points. You always need 2 points to find a slope. x1 f of x1, in this case that's 1, 1, and x plus dx f of x1 plus dx. As long as we choose dx less than 10 to the negative 6, threshold value, we get the same answer. Whether we choose dx equal 10 to the negative 6, 10 to the negative 7, or 10 to the negative 45, the calculated slope remains the same. This illustrates the concept of an infinitesimally small change in calculus. Dx is an infinitesimally small number. How small is dx? It's as small as you want it to be. No matter how small it is, you get the same value for the slope.
AcePhysics.org, Math and Physics Tutoring with Dr. Hudis.
Finally, we'll move on to example 3 involving the definite integral. Example 3. Infinite sum of infinitesimally small pieces. The definite integral is defined to be this sum. This integral is equal to this sum. The integral from a to b of f of x dx is approximately equal to f of a dx plus f of a plus dx, that multiplied by dx, plus f of a plus 2 dx multiplied by dx. We just had a small power surge. It's snowing outside. This approximation becomes increasingly accurate as dx becomes smaller, and in the limit, as dx is infinitesimally small, the sum converges to the exact value of the integral. Given the function f of x equal to x squared, a is 1, b is 2, and dx is 0.1, the definite integral can be approximated as this sum. This is a sum with 10 terms. The first term is f of 1 times 0.1. The second term is f of 1.1 times 0.1 plus f of 1.2 times 0.1 plus all the way up to f of 2 minus 0.1, which is f of 1.9 multiplied by 0.1. F of 1 is 1 squared, f of 1.1 is 1 squared, and so on. If you sum up all these numbers, the approximation you get for the 10-term sum is 2.185. If dx is chosen to be 0.5, then you have 20 terms in your sum. And for that sum, now the approximation for the integral is 2.258. Now if we take dx equal to 0.01, we get 100 terms in our integral. And the integral is equal to 2.318 with 100 terms. On this slide is a table. The first column of the table is dx. It's the size of dx. dx is also called h. The second column is n. This is the number of terms in the sum that approximate the definite integral. And then we're looking at the definite integral from 1 to 2 of x squared dx, and these are the values of the approximation. If dx is equal to 0.1, there are 10 terms in the sum, and you get 2.185. If dx is equal to 0.05, it's half as big. There's going to be twice as many terms in the sum. Now you have a sum of 20, and the integral is approximately 2.258. Once you get to 200 terms and a dx of 0.005, the integral is 0.232. For this case, dx is of 0.001 is the threshold. There are 1,000 terms in that sum, and the value for that is 2.333. There might be more numbers after that. Imagine your measuring equipment only has accuracy up to 3 decimal places. Any dx smaller than that produces the same number. So if you use, any sum with more terms than 1,000 will give you the same answer for the definite integral. There exists a threshold value of dx below which the calculated integral value is essentially the same. Consequently, any h value smaller than this threshold will yield an equivalent integral value. Key takeaways from example 3. The definite integral is a sum. This is just an important formula from calculus that you simply should memorize. As the value of dx decreases and n increases, n is the number of terms in the sum, the value of the definite integral changes significantly when dx is large. There exists a threshold value of dx below which the calculated definite integral is essentially the same. Consequently, any dx value smaller than this threshold will yield an equivalent value of the definite integral. Dx is infinitesimally small. It's as small as you want it to be, and the integral will not change. No matter how small you choose it, or how many terms you put into the sum, you'll get the same value of the definite integral. Dx, how small is dx? It's as small as you want it to be. It's infinitesimally small.
AcePhysics.org. Math and Physics Tutoring with Dr. H. AcePhysics.org. Math and Physics Tutoring with Dr. Hudis.